Good evening to all. Can you all hear me?
Yes.
Thanks.
We can hear you.
Thank you, madam. I'm Lalit Pallegam, Chairman of Civil Engineering Section Committee of ISL. Today, we are going to talk about Eurocodes for steel structures in Sri Lanka. Before I introduce today's our resource person, I would like to emphasize, what is the importance of this topic, because when we read the introduction of this lecture, I found Eurocode as established 2010, now 2021 actually. So why then do we not adapt the Eurocode with question mark? That's very big question we all have, but we know some constraint and a lot of things to do to go that point. So that's our target as a Civil Engineering Sectional Committee, to enhance our engineers' knowledge and awareness on this matter. But we cannot definitely we cannot learn all this within these 2 hours. Only this will be an eye-opening to this subject actually. That's our target as a ISL, as a Civil Engineering Sectional Committee, and with request of Madam Dr. Premini Hittiarachchi also. I think she also has same view. So today our resource person is Dr. Mrs. MTP Hittiarachchi. She's as an element of University of Moratuwa. After successful completion of postgraduate studies from Imperial College of Science and Technology, University of London, she returned to serve the University of Moratuwa. Since then, Dr. Premini Hittiarachchi has been actively engaged in teaching structural design and at undergraduate and postgraduate levels, and research and consultancy in construction material and structural design. She is responsible for introducing the latest revisions to Code of Practice, including the Eurocode recommendations in timber and steel, to the undergraduate and postgraduate curricula at the University of Moratuwa. Her primary research interests are in the structural use of timber and steel. Much of her research is of a Sri Lankan context and has been published in local research proceedings and journals. She has contributed much to continuing professional development of structural engineers by serving as a resource person on short courses organized by University of Moratuwa and Society of Structural Engineers. That's about our resource person today. I think we all can learn and we all can aware about this subject. Over to you, madam.
Thank you. Okay, can I share the screen now? Can you all see this screen? So, Eurocodes for steel structures in Sri Lanka. During this presentation, I hope to answer questions that you might have relating to Eurocodes. So before we proceed, let's remind ourselves what codes of practice are meant to do. They are guidelines that give the current state of knowledge relating to materials and components, structural loading, the proportioning of structural elements in a specific material, and the design of special structures. And structural designers use codes of practice to design structures. Now, the codes maintain a balance between accepted practice and recent research. The code writers distill the recent research in a manner that can be of use to the designer. But codes don't cover every aspect of design. Some areas of design cannot be quantified in the manner required for codes. Some areas are rarely encountered in practice to be included in design codes, and some areas are included in textbooks and handbooks, so they don't include that in codes of practice. But the bottom line is that the responsibility of the design lies with the designer and not with the code authorities. So structural engineers in Sri Lanka use British codes of practice, or have been using British codes of practice over the years, to design steel structures. I remember when I was a student, we were taught BS 449, which was based on the allowable stress method. And when I began my teaching career, the limit state design codes had made their appearance in the world, and BS 5950 was introduced to this country. And we have been continuing to use BS 5950 with about a couple of revisions to the code. So BS codes have now moved to Eurocodes. And let's see why or what happened there. So at the end of March 2010, British codes of practice were withdrawn and superseded by an entire set of Eurocodes. And no further revisions will be made to that standard. It doesn't mean that the standard is not safe, but it means that with time, it will become out of date and no longer be current best practice. So there are no further revisions to British standards. Instead, what they have done is they have adopted the Eurocode and they have moved from a BS to what is called a BS-EN. EN standing for Euro norm. So what you have is BS-EN 1993, which is the steel code. So why Eurocodes? It's to improve trade of construction products and services within the European Union by providing common rules for calculation and design. It also serves as a basis for reference, giving the best possible scientific advice, and it improves competitiveness of the European construction industry by offering advanced concepts of calculation and design. So put in a very simple fashion, what they're saying is that it's possible to design a structure in one EU country for erection in another country. The use of common rules enables designers to work in other European countries without having to learn new codes. So that's a big advantage. And of course, the most important advantage is that all research carried out in the European Union countries can be combined into one set of design requirements. So put in a nutshell, it's a common basis for technical and scientific collaboration. So what is in it then for us here in Sri Lanka? I believe it's a complete set of up-to-date design standards that include the main construction materials, fields of structural engineering, and a wide range of structures, while at the same time, it retains the flexibility of meeting local needs and best practices with regard to levels of safety, loading, and durability in the form of national annexes. So what does a national annex include then? It includes mainly, or firstly, the nationally determined parameters, also referred to as NDP, that can be adopted in the relevant country. So there are certain parameters that Eurocode says you decide for yourself what you want to use in your countries. Guidance on the use of informative annexes. There are annexes to the Eurocode and there's guidance available in your national annex, which tells you how to use it. And there's also reference to what is called complementary information, supplementary information, which is of a non-contradictory nature that can help the designer to apply the Eurocodes. So these three aspects are included in the country's national annex. Now, what is the implication then by the withdrawal of the BS codes for structural designers in this country? Do we develop our own suite of Sri Lankan national codes or do we adopt the Eurocodes? Now, developing a national code requires a great deal of time, effort, and resources, which we can ill afford as a developing nation. So very prudently, very wisely, the Sri Lanka Standards Institution decided to adopt the Eurocodes, and they have drawn up the relevant national annexes. And in particular, I am aware that the steel structures national annex is ready. Now, this was the title of a presentation that I made to the Society of Structural Engineers way back in 2010, almost 11 years ago, or more than 11 years ago, at a question time. Eurocodes in steel are here. Are we ready? Actually, I borrowed it from an article I had read at the time. And I must say that at that time, we were not ready. Okay. But now, in the intervening 10 years or 11 years, much has happened. And I would say with confidence today that we are now ready to adopt the Eurocodes on steel. National annexes have been prepared. Training has been provided. We have run short courses, but for the past 5 years or so, we are training our undergraduates at Moratuwa. And I know Moratuwa followed the other universities, Peradeniya and Ruhuna, for a fact, I know they started before us. So undergraduates are now learning the Eurocodes, not the BS codes. Then even the postgrads are being taught the steel Eurocode. There's computer software that is available. Then there's plenty of guidance in the form of textbooks, specialized publications. And I'm taking this opportunity to also refer to a textbook that I have written jointly with Isuru Nanayakkara, which gives the background, the theory, gives you worked examples, and it also gives some helpful flow charts. So it's an inexpensive text, introductory level, for anybody who's interested in learning the more further details of the Eurocodes. Obviously, I'm not going to be able to explain the use of Eurocodes for steel during this short period, but so there is plenty of guidance available, even on websites. So what then are Eurocodes? Now, Eurocodes are a suite of 10 documents, main documents. There are 2 documents which intend using, and then there are 6 that are material related. And also there's 2 more, which is the geotechnical design code, which is Eurocode 7, and the one that deals with earthquakes or seismic actions. So you can see the link between the Eurocodes. Now, EN 1990, which is the basis of structural design, which was first published in 2002, is a world's first because it's a material independent design code. Up to that point, all design codes were related to some material or another. But here is a code which has been written with no particular material. And it's a core document that gives the principles and requirements that relate to safety, serviceability, durability, and robustness for designing buildings, bridges, towers. When you say towers, it includes masts, silos, chimneys, so whatever. Now, the basic requirements have what they call principal rules and application rules. Now, in the case of principal rules, you have to stick to those rules. You can't make any changes. But in the case of application rules, you can use some other method as long as you can justify that the requirement is met. So take, for example, potential damage shall be avoided or limited by appropriate choice of one or more of the following. One of the items says, select a structural form and design, that's what I have boxed here, that can survive adequately the accidental removal of an individual member or limited part of the structure or the occurrence of acceptable localized damage. And that's exactly what happened. On the right, there is this little picture, photograph of Charles de Gaulle Airport in France, where part of the terminal building collapsed. But the damage was limited or confined to this restricted length of building, and that was since repaired, obviously, and the terminal building could be used without further delay. So that is an example of where the structural form was able to cope with this damage, which was contained within a a particular location. Then we say here, avoiding, eliminating, or reducing the hazards to which the structure can be subjected by selecting a structural form which has low sensitivity to the hazard considered. And if you take that of wind and you have tall buildings, you as structural engineers in the audience, you would know that there are ways that you can mitigate the effect of this wind on tall buildings. Then this code, this BS 1990, the code document, gives you the categories of design working life, and they give you different examples. So monumental structures, iconic structures is about 100 years. Now this is something as an example of a nationally determined parameter. So we in Sri Lanka can decide to change this if we wish to, right? In the UK, they have done this. The 100 years has been extended to 120 years in the case of monumental structures. The ultimate limit state and the what you call it serviceability limit state are the same limit states. Eurocode sticks with the same limit states. Now, some of the terms they use are different. So they don't refer to loads, they call them actions. So you don't have dead loads, but you have permanent actions. Then all of your imposed loads, wind loads, snow loads, they are referred to as variable actions. They can vary over time, space, whatever. So, and then they have accidental loads. So accidental actions, sorry. So variable loads are then, or variable actions, sorry, can be subdivided into imposed actions, those due to people, furniture, storage, and there is the wind and the snow. So these are the actions on the structure. The philosophy of structural design obviously remains the same, and it means that the design action, which is the characteristic action enhanced by a factor of safety, has to be less than the design resistance, which is the characteristic resistance divided by a partial safety factor, that for materials, right? So the concept or the principles of structural design are the same. But only thing is these numbers, these gamma F and gamma M and so on, are now a little different from what we perhaps have been or what we are familiar with. So firstly, how do we combine actions? So you have your permanent action, as the name suggests, it's permanent, and you combine that with variable actions. The photograph that I have shown you is the Millennium Gateshead Bridge in the UK. And it shows you the bridge with no people on it, and then with so many pedestrians on the bridge. So how do we combine this? Now, EN 1990 gives you two methods. This is the code document still that we are talking about, right? And the two equations are, you have 610, which is the fundamental equation. And then you have another pair of equations, 610A and 610B, and you have to select the more onerous of the two, the worst condition of those two equations, right? Alternative expressions. You can use either 610 or you use 610A and 610B and take the worst condition. It's not that you have to do all three, right? So it's only 610 or 610A and 610B. So let us look at these partial safety factors. I will explain this in, the equations look rather frightening, I must admit, but they are not as bad as they initially seem to be. So if you take this actual small print there, but I gave you the entire page that is in an annex to EN 1990. So it says that the gamma G value, that is the partial safety factor applied to permanent actions, is 1.35 at its maximum and 1 at its minimum. And gamma Q is 1.5, that is a variable partial safety factor for variable actions, and is 0 at its minimum. So you can see they have clipped a little bit of those numbers that we are familiar with. We had 1.4 GK and 1.6 QK in the BS, right? So now the 1.4 has reduced to 1.35 and the 1.6 has come down to 1.5. Then on top of that, there is another term that they have introduced called the psi factor, which is called the combination factor. I'll talk about that a little later. And there is another one which is introduced to the permanent action. There again, we can decide it's a nationally determined parameter, that particular value. 0.85 is what the European the code recommends, but in the UK, they have increased it to 0.925. Right. So when we talk of the partial safety factors, like I said, we have 1.35 and 1.5, right? And the combination factor is a factor that is introduced to reduce the load when it's in combination with other variable loads. And that value is usually 0.7. And the exceptions are for a storage area where this load can be anticipated to have its maximum value throughout its life. So you take that as 1. And in the case of wind, you take this combination factor as 0.5. Right? So what the code in effect is doing is, when you look at this equation 610, it's taking the sum of factored permanent loads, permanent actions, and then it is taking one of the variable loads at a time, right? So it's saying the factored leading variable load, and that is multiplied by that 1.5 factor. But the other variable action, say it's wind or snow or whatever other actions, you use a combination factor. So it is the same effect as, like, if you remember, we had 1.2 GK, 1.2 QK, and 1.2 WK. So it's the same story, but put in a more consistent fashion. And I think you'll explain that. You will under simple examples. So on this one, I just have a flow beam, and I have 1.35 into 10 plus 1.5 into 12. That is, 10 is my dead load or permanent action, and 12 is my imposed action. So 1.35 into 10 plus 1.5 into 12 gives me 31.5. So very simply, the design action is 31.5, right? But if I were to use 610A and 610B, what I am now doing is introducing this combination factor into the imposed load. So that reduces to 26.1, but you can't get away with 26.1. You have got to use the 610B, and we find that that gives you 30.5. In 610B, the leading variable action is taken to its maximum, but on the permanent action, they're reducing it marginally, and in the UK, they're using 0.925. So you can see there is a marginal decrease by using 610A and 610B. So extra effort, but what you're getting out of it is, I would believe, hardly worth it. And I would stick to 610 if you were to ask me. Right. Now, what is interesting is when you have the wind also contributing. So let us take a roof truss, a steel roof truss, which perhaps is subject to, due to permanent actions only, a particular member, let us say, carries 4 kilonewtons in tension. Due to imposed loads, as people working on the roof or repair or whatever it is, let us say it's subject to 2 kilonewtons in tension. And due to wind, also in tension, there'll be 3 kilonewtons. So when you combine this, you have to take the leading variable action. So in the first instance, I'm taking the live load as the first variable action, leading variable action, and the wind I'm reducing it by a factor of 0.5. So I have an answer of 10.65. The next thing you do is, now you take wind as the maximum, and I have 1.5 times 3 and 1.5 times 0.7, because that's a combination factor for live load, and I end up with 12. So obviously my design action would be governed by the wind more than the live load, and I have a design action of 12 kilonewtons, right? Now, when it comes to wind, which is opposing it, supposing we have the 4 kilonewtons that we had before and the variable action of 2 kilonewtons in tension, but wind causes compression, let us say, of 3 kilonewtons, right? In this case, here we see dead and live load combined together, 1.35 into 4 plus 1.5 into 2. But when you have the wind is actually open. Gamma value for wind is 0. So you have here now 8.4 kilonewtons is the maximum tension force. And when you have wind as the leading variable action, you find that the permanent action has to be minimized because the two are opposing each other. Permanent action is tension, wind action is compression, right? So you take the minimum value for permanent actions, which is 1. So you see the different gamma values. This is simply the 1.0 GK and the 1.4 WK, which you're used to, right? So previously in the BS, they specified those different combinations and those factors. Here they are giving it in one statement, and you have to adopt it or adapt it to suit your particular situation. So it's like when the wind is very high, you won't have men working on the hello, I'm at a lecture. Can I call you back? So that is what's happening in the case of okay. So when the wind is very high, you will not have men working on the roof, and similarly, the men will work on the roof when wind is at the same time. So this is where the combination factor comes into its role. Serviceability criteria is not defined in the Eurocode. In other words, it says it should be specified for every project on a case-by-case basis and agreed with the client. So it tells you what you mean by vertical deflection. It tells you what is meant by a horizontal displacement, but it does not specify any limit. So you have to look for it elsewhere. Then we move on to the second Eurocode that we need to use, which is that to do with the loadings, or in the Euro speak, it is actions. So there are 4 different codes that deal with actions. You have that which is called the general actions. You have one dealing with the traffic load on bridges. You have another for cranes and machinery, and you have a 4th one for silos and tanks. Now that first one, which is general actions, is again subdivided, or there are subparts, 7 of them. So the first one is the one that we are most, or we should become most familiar with, which is the one that gives you the weights of all the construction materials, densities, self-weight, and so on, as well as the imposed loads. Part 2 deals with fire. 3 deals with snow, not a problem in this country. But the next one, 4, is of great importance. That's the one that deals with wind. So when you're designing a structure, we would need to have EN 1991, 1-1, as well as 1-4. Then there's thermal actions. There's actions during execution, that is the construction. They use the word execute for construct, and accidental actions. So there are these 7 parts of the actions code that we need to be aware of. So if I just have a quick peep at the EN 1991-1-1, this has all the densities and self-weights of construction work, as well as the imposed loads are specified for different categories of buildings. So if you have a residential building or a domestic building, you have office areas, then you have areas where people congregate, shopping areas, and also what do you call them, storage areas. E is for storage. The category C is again divided depending on the gathering of people. So you might have something like a restaurant. On the other hand, you might have a place like a stadium where there's a much greater number. Now we move on to the steel code in itself. And I have deliberately selected an icon which shows you many, many volumes, because that is really what steel code is like. You have a whole number. I think it's almost 60 or 58 documents if you were to count it all up. Right. So it is subdivided into 6 parts. Part 1 is what we are mostly concerned about, which is the general rules and rules for buildings. Then there is another section which deals with bridges, a third one to do with towers and masts, silos, tanks, and pipelines are yet in another one, piling, and then we have cranes supporting structures. Now, the first part is again divided into 12 parts. And of those 12, the steel code that we are most familiar with would be 1.1 or 1-1, which is the general rules. And also part 1-8, where the joints and connections are dealt with separately. It's a separate document. So in order to design a steel structure, we need to design its members, and we need to connect those members together. So we essentially would need to look at 1-1 and 1-8. But depending on your structure, you might need to refer the other documents as well. So fire, for example, is in 1-2. Plated structural elements like a plate girder, if you were to design, say, a bridge girder, you have to use 1-5. Fatigue is a problem, then you have to look at 1-9 and so on. So there are these other parts so there are 12 such parts which all contribute to these general rules. But you don't need all of them for a very basic structure. You can get away by using 1-1 and 1-8. Right, so if I have a quick glance at the contents, we have the general basis of design, materials, durability, structural analysis, and then the 2 limit states, ultimate limit state and serviceability limit state. Now, there are certain parts of this that I would like to highlight or draw your attention to. So I will describe that in greater detail in the slides to come. But in this first slide, I want to show you the axes. Now, the Eurocode refers to the major axis as the YY axis and the minor axis as the ZZ axis, right? With the XX axis being the axis along the length of the member. So that could be confusing to us who have grown up using XX as the major axis and YY as the minor axis. But if you're starting afresh, then of course, you get accustomed to, okay, YY is the major axis, ZZ is the minor axis. Then section properties, the terms that they use also are a little different. For example, section modulus, they use the word W. And elastic section modulus is WEL, and plastic section modulus is WP, right? So there are, small changes that we have to, get accustomed to. Axial forces are denoted as N, bending moments, the symbol M, and the shear forces by the symbol V. Then global analysis and materials is something I'll be describing in greater detail in the next slides. So in terms of materials, we have 4 grades of steel included in the Eurocode. Those who are familiar with the BS code, we started with S275. That was the lowest grade of the steel. So this, I believe, is a big advantage for us, right? So as long as it complies with the specification, the Euro norm 10025, then we can use S235, or you can continue our calculations using the corresponding strengths of S235 as opposed to S275. So if a steel does not meet the specifications of S275, but they meet 235, then we don't need to reject that steel. We can still use it, but use a lower strength as given here. Right, so that I feel is one advantage of the Eurocode, which we didn't have in BS 5950. Then comes this global analysis. So like that guy is holding his head, you might wonder what's happening here, right? So when you perform your analysis, you have to look at the geometry of your structure and also the material properties of your structure. So when you look at the geometry of your structure, you know you apply the loads and the structure deforms. But what you do is you continue to apply those loads on that undeformed structure. Or in other words, you say the deformation is so small, it's not going to have an effect on your structure. But certain structures might be rather slender. They might be subject to swing action and so on. And those give rise to secondary effects. So those deformations are not small enough to be ignored. So then we have to do what is called a second order analysis. So more complicated, but it correctly simulates or represents what's happening to that structure, right? So you can have either a first order elastic analysis or a second order elastic analysis. Sorry, a second order analysis with relation to geometry. When you talk about the material, fortunately steel is a linear elastic material up to a point, and then it yields. So then we look at the plastic hinge cause it to collapse, right? So we can either use elastic analysis, linear elastic analysis, or we can go for a plastic analysis. So you can see that there are 4 possible combinations that we can use in our analysis of the structure. And again, the code guides you on whether you should be using a first order analysis, or they alert you to the fact, okay, beyond this, you should not be using a first order analysis. So you have either got to change the stiffness of your structure, or you have to look at the secondary effects, what we call the P big delta effects and the P little delta effects. So they are considerable, and therefore you would need to carry out what is called a second order analysis, right? So this is very informative in that sense. Then we have this question of local buckling. That is because steel sections are made up of very thin sections, right? I'm not talking of cold form sections, even your hot rolled sections. And those plates, when subject to compression, could buckle, plate buckling, right? So this problem of local buckling taking place before the section fails in another way, either in bending or in compression or whatever, there will be the localized crumpling or the plate buckling, right? So we have to classify a section depending on whether it is in the BS, the terminology used was plastic, compact, semi-compact, and slender. In the Eurocode, they refer to these as 1, 2, 3, and 4. So class 1, class 2, class 3, and class 4 corresponds to the slender section. So there again, it's very similar to the BS. They give you the limits within which you have to work if it is a non-slender section, right? Now, this is a very important factor, the partial safety factors for steel, right? They have introduced 3 different partial safety factors. Gamma M0, which deals with the yielding aspect, gamma M1, which deals with the instability aspect, and gamma M2, which deals with the fracture or the rupture. Now, gamma M2 is 1.25 as recommended in the Eurocode, whereas gamma M0 and gamma M1, they are not as dangerous, so they are taken as 1 or the actual value. Now, the UK National Annex, they use the 1, obviously, and in the case of fracture, they bring it down to from 1.25 to 1.1. Right? Now, we in this country, we are sticking to 1.25. We are not sure of the quality of the steel. We are not getting steel from Britain, right? Britain is very sure of their steel. And if you would recall, I alerted you when we used BS 5950, they take the design strength as the actual yield strength. In other words, the partial safety factor on that steel was 1. Right? And they developed all their charts and their tables using this partial safety factor of 1. But when you have steel, which is perhaps of not of that same quality, right? Or you're not sure of the quality of your steel. There's a greater spread of results. Are we happy to use this partial safety factor of 1? Right? So I'm not sure what you people did as practicing engineers, but I used to alert you when I was teaching BS 5950, well, actually to the to students at Moratua. Now I can be happy because now you have a value of 1.25. So that looks after any discrepancies in quality. So one of the strength divided by 1.25 means you're actually multiplying it by 0.8, right? So you're taking 0.8 of its ultimate strength. And there's also more focus on formulae rather than on tables and charts. So in the British codes of practice, or in the older codes of practice, before we had spreadsheets and computer software and so on, we had all these tables and charts that designers used to look up to do their designs. Today, we don't need to do that because we have software, or we have spreadsheets. The computational facilities are available, so we can use equations, and most of the later codes actually include the equations as well, and this is what Eurocode has done as well. And so there is an explicit reference to the partial safety factor. So these partial safety factors are nationally determined parameters as well, and we have going with the European recommendations. Most of our other recommendations, we stick with the British because that has been our practice before. But in the case of the partial safety factor, we remain with the recommendation given in the European Code of Practice. Now, EN 1993 1-1, that is the steel code, is based on structural behavior, right? So there is one section that deals with all the resistance aspects. So whether it's bending or tension or compression or shear, all the resistance parts are given together. And stability is dealt with in a separate section. So you have buckling, lateral torsional buckling, and so on, dealt with separately. So there is more responsibility now on the designer to identify the correct mode of behavior, right? Unlike in BS 5950, you had a recipe book style. Okay, if it's a beam, do this, do this, do this. If it's in compression, do this, do this, do this, right? So this is an essential difference between BS 5950 and the European code. The Eurocode EC3 is the one that deals with steel. So it's also called EN 1993 or Eurocode 3. So the layout of the document is such that there is no direct set of rules for the design. Has to find the rules for each type of behavior and make certain that all the aspects of the design are covered, right? So if it's tension, you have to find out how will this fail in tension. If it's compression, how will it fail in compression? If it's bending, shear, torsion, whatever, you have to find out how does it fail, and then look for those particular rules within the code. It's all there, but it's not sort of given in a flow chart form. Right, so let me take you very quickly through these different behavior, but of course not going into great detail. But if you take tension members, they are the simplest to design. You must make sure that there's enough area and there's enough strength. So in the case of steel yields, right? It elongates with no additional stress in it, right? So there's two aspects. It can yield too much or it can fracture. Fracture, why? Because due to the presence of bolt holes. So there are two checks that you need to do and take the smaller of the two. So very straightforward. I think all of you now in the audience, if you know what you're doing, you can design a steel tension member. So you have the area, you have the yield strength, you know the grade of steel, you know the yield strength, divide by gamma m naught, and you have the plastic resistance. Now that, or you might have a very vulnerable section at the bolt holes. So you take a net, that is the net area at the bolt holes, but not even that, you take 90% of that into the ultimate strength divided by gamma m2, where gamma m2 is now 1.25. Angle sections are dealt with separately, and for that you have to refer the joints code, the EN 1993-1-8, right? So angle sections subject to tension are dealt with separately because of the eccentricity of the load. So there is an inherent eccentricity because the connection does not coincide with the centroid. So we have an easy way out, and that is dealt with separately in another, actually another document. Okay. Now, when it comes to compression, there is the resistance aspect and the stability aspect. Okay. So again, we have got to go through the stability part of it. And there again, it's very neatly put. You say compression resistance is the strength multiplied by the yield strength, Fy upon gamma m naught. And the buckling resistance is that same value, but now reduced by a certain factor, right? And we know that buckling depends on the slenderness of the section. And if you look at the Euler buckling curve, you see here the bottom curve here that I have drawn. This curve will tend to infinity. Mathematically, it will tend to infinity, right? As the slenderness gets less and less, this carrying capacity keeps increasing. But it's curtailed, it's limited by the fact that it will crush before that happens, right? So that value where the crushing and the buckling load are the same is referred to as a slenderness lambda 1. And we introduce the slenderness called the non-dimensional slenderness, the actual geometrical slenderness of your section divided by this lambda 1. So in other words, this curve is drawn again where the non-dimensional slenderness, this value is 1. And why do we have separate curves here? Because Euler buckling curve is a theoretical curve. It doesn't take into consideration the real behavior due to imperfections and so on. So we have to therefore cater for those, and that is where we look into, and also the axis about which it will buckle, the type of section and so on. So there are 4 different curves that are introduced. Of course, I'm showing you the curves here. The curve is included in the Eurocode, but they have also given you the equations that lead to these curves. So you can use those equations and come up with more precise values than just reading off this curve. But one thing the Eurocode has not included is in determining the slenderness, it does not give you the effective length values, right? If you will recall, if your 2 ends up in, what we say is, it's the effective length is the actual 7 times the actual length. Now the Eurocode does not include that. You have to look for it elsewhere. So if you are an experienced designer, it comes to you. If you're not, then you have to look into a handbook or a textbook or some sort of guidance to find out what the effective length should be for your particular end conditions. When it comes to a beam, again, the code talks about resistance. The code talks about stability. So the resistance is bending, shear, and bending and shear. And then we have the stability, the lateral torsional buckling. So there are 3 different ways this beam can fail. But there are actually 6 different ways a steel beam can fail, right? So what can go wrong? Firstly, you can have local buckling in compression. That is what is shown at the top one. You have a few wrinkles at the top. So it can fail in local buckling. It's not listed here, but that is one of the forms of failure. Then there is bending failure, shear failure, and lateral torsional buckling, again, because of the fact of compression. I'll explain that in a little greater detail later. Then there is also bearing or web crippling failure, right? Because when the load comes right through the web, which is a slender, thin section, that can cause buckling or it can cause crushing. So that's a problem. And you have excessive deflection, which is a serviceability limit check. So the code doesn't take you through this. You have to identify, okay, how does the beam fail, and look for it in the code. So that's what I'm trying to impress upon you. Okay, so when it comes to the resistance checks, the local buckling check and the bending resistance are combined by first categorizing it into a class 1, 2, 3, or 4, and then using the appropriate formula for it. So if it's class 3, that means it can't become plastic. Between that elastic region and the plastic region, the section has buckled locally. Right? So then you would use only the elastic section modulus in working out your bending resistance. When it comes to shear resistance, it's virtually the same thing that we BS 5950 was using. After all, steel behaves in the same fashion. It's just that we learn a little more about it and try to include what we know about it in a fashion that is, what shall I say, easier to absorb, or more of a realistic nature. We represent it in a more realistic fashion. So if you take this, if you remember your equation for shear resistance, it was 0.6 py times the shear area. Now 0.6 py is the design shear strength of the steel. Now here, instead of 0.6 py, we use Fy upon root 3. And anyone who does that arithmetic will find that that comes to 0.58, which is near enough to 0.6, right? And of course, gamma m naught is 1. So it's put in a different way, because the root 3, I believe, can be argued or justified using what do you call it, stress criteria methods. Then AV is the shear area, which in the case of BS 5950 was simply the web depth into the thickness. But here there is a little more that is, or rather, it comes out almost the same, because you don't take the overall depth, you take the depth between the flanges, and then you take a little more, half the thickness of the flange and the root radius, that little part, and again at the bottom, similar part. So there's a simple equation which will give you the web area, sorry, the shear area. So it's virtually the web area, right? When bending and shear combine, that is when you have a high shear situation, if you would recall, the limiting point was 0.6 in the BS. Here they limit it to 0.5, and they use a reduced design strength. So 1 minus rho times Fy is what is used, where Fy is, rho is defined for you, right? So that's quite straightforward. Then this question of lateral torsional buckling. Lateral torsional buckling occurs because there is compression in one part of your beam, and there's tension in the other part of the beam. So the compression part wants to buckle. The tension part says, no, I want to remain straight. So there is this twisting action, right? So the lateral load from the compression, there is the lateral load from the tension, which causes this twisting action. And that phenomena is called lateral torsional buckling. And it is dealt with in the same fashion as that you deal with buckling in compression. So you have a similar set of equations from which you can derive what is called the buckling resistance moment, right? So they are very consistent in that. So they have the same sort of formulae to work out these details. Then there is the web buckling and bearing that I spoke about earlier, and that's more common in very deep sections. So that's plate girders. So they have included that under the plate girder section. So that only happens if you have a load which is transferred via the flange to the beam, right? So you can have a column stopping off like in this photograph here, or it could be where the beam is sitting on something else, supported on something else. But if you just have a secondary beam meeting the column, the beams just meeting the column through the entire web, then of course the web doesn't buckle, right? So you got to look at the appropriate code of practice for that. In the case of deflection, I repeat here, there is no guidance given, and the UK national annex, they go back to their original values. Where the brittle finish is span upon 360, where it is all other beams, they say span upon 200. Brittle finish, there's a more stringent limit, and cantilevers, you use a limit of span upon 180. This is what the UK National Annex recommends. So we can, I don't quite recall what we recommended in the Sri Lankan National Annex, but you can decide on it on a case-by-case basis. If there is no guidance, okay, you can decide to use these as your guidance. Then combined bending and axial forces, that's a bit of a tedious calculation, but they take you step by step. So sometimes at first glance, these equations look rather frightening, but if you digest it little by little, then it's actually not as bad as it looked at the first glance. So this is from a structural blog that I was going through. There's heaps of information on the websites. So it's not difficult at all, because remember, European Union is so many countries, so all of them put their information, and so there is a shall I say, a plethora of information that you can gather details from. So these were interesting flow charts relating to tension members, compression members, and bending members. Of course, it doesn't talk about lateral torsional buckling as such here, but yeah. Right, now moving on from the elements to the joints. So steel structures are designed so the constituent steel member elements can safely resist the design actions, and they must also have a deformation capacity that is consistent with the assumptions made in the global analysis. So if you assume a rigid joint means no rotation possible, you have to ensure that that rotation is not possible. So you can't have a joint like this, right, and then have it fail like that. So you have got to make sure that that rotational capability or the ability not to rotate is maintained. Similarly, if you're talking of a roller support or a sliding support, sliding joint, then give it the sliding joint, because otherwise there will be a catastrophic failure if you don't allow it to move, right? So in the case of steel, you give slotted holes. Now, when you provide a slot, it's not just enough to provide a slot, but you must ensure that that displacement that you calculated and that support can be accommodated by this slot. So there is more to than just analysis and looking at the maximum deflection or the maximum rotation or whatever it is, but you have to ensure that all those little assumptions that you made in your analysis are now proven in your design, right? So rotational movement allowed at a hinge. If you have said it's a hinge and you're allowing rotation, then detail your connection so that it's able to move. If it's a pinned base, then make sure that it's a pinned base, right? So that those connections must satisfy the requirements of structural behavior. So BS 5950 says something of this nature and then doesn't go beyond it. But the Eurocode, you will discover in the next few slides, goes into a lot of detail into this aspect of it. So resulting moments and forces depend not only on the deformation capacity of the individual beams and columns that make up the structure, but also on the joints between them, right? So here we are, when you model a structure, analysis, modeling and design of joints, we are used to, okay, there is a frame, you decide on the member sizes, you decide whether your joint is a simple joint or a continuous joint, then you go on to do your analysis and come up with your sections, check whether they are safe, and then you go to do your joint design. And then you might discover that what you assumed originally as a simple joint is not quite a simple joint. So you have to redo this analysis and redo everything that you did, maybe several iterations of this nature. But the Eurocode gives guidance so that you don't need to go through these repetitious calculations. Now we know that a simple joint means that there is no bending moment capacity and that rotation is possible, right? So it's on a moment rotation curve, it is this green line. Similarly, if it's a rigid joint or a continuous joint, it means that there is no rotation possible, right? Zero rotation, but it's able to carry a certain bending moment. So it's this vertical line. But in reality, neither of those exist. So you might have a joint which is close to a simple joint, not exactly a simple joint, and similarly a continuous joint, but not really it's not exactly a continuous joint, right? So the chances are we are in this intermediate region of what we might call semi-continuous situation, right? So here again, the code is very specific. It helps us. It says, okay, your stiffness could be either pinned, rigid, or more likely semi-rigid. Your resistance could be full strength, partial strength, or pinned. And it's only in the pinned situation that you can consider it as simple, right? Or if it's a stiffness and resistance, the stiffness is rigid, and if it's a full strength joint, yes, then it is continuous. Anywhere in between is a semi-continuous situation, right? So how do you decide what is rigid, what is full strength, what is partial strength? The code gives us limits, very specific situation. So pinned is if EI upon L, where EI upon L is the flexural resistance of the connected beam, or flexural stiffness really of the connected beam, right? Over here on this side, on the strength side of things, if it's pinned, it means that the capacity of the joint, the resistance of the joint is less than 25% of the full strength of the weaker connected member, right? So there is specific guideline. So then you might say, okay, we can work out, how do you work out the strength of the joint? How do you work out the stiffness of the joint? So there again, the code is very helpful. But before I go on to explain that, so here we have a consistent approach to the design of steel structures. At your preliminary design stage itself, when you're working out your section sizes and so on, and you feed that into your software, you can use the stiffness and the rotation capacity and the strength and so on of your joint. So you design an approximate joint and you give the details of that joint so that you're then modeling almost realistically the actual structure. So you might have to iterate, but certainly not as many times as before, right? And your assumptions will hold good. So Eurocode 3 part 1-8 also has 7, what shall I say, chapters or 7 sections. And something that I'd like to draw your attention to is the fact that they include hollow section joints, or joints made with hollow sections, tubular sections, which is new, right? BS 5950 didn't have that. You had to refer to some special document if you were designing a structure with hollow joints. So that's something new. Now, bolts is contained in chapter 3 and welds in chapter 4. So a bolted joint in shear, or when a bolt is subject to shearing action, it can fail with the bolts in shear. So there is a straightforward equation there. And the bolts could also fail in bearing, where the bolt rests on your plate, and therefore it can fail in bearing, or the bolt itself can fail in bearing, and it can also tear out. So the BS also gave the same equations, and you check each one in turn. Here we just include a coefficient. You take the lowest value corresponding to each of those different failure modes, and that is my alpha. Similarly, when you have a number of bolts together, they will interfere with each other, perhaps in this bearing resistance. So there is this material confinement, and there is a K value that is introduced. So it takes care of that. And you have the bearing and the shear resistance, but this is for a single bolt. So if you have a group of bolts, you multiply by the number of bolts. But there is also another aspect. This is block shear, right? Block shear means that entire group of bolts can shear out. not only shear, it will rupture as well, right? So there is a combination of rupture, tension, and shearing. So this is something that they discovered when they looked at maybe failures in steel connections. And the Eurocode has included it, as well as those who are familiar with the latest revision to BS 5950, the 2000 version. This is something that was included there. So in other words, when all the European, these experts got together, they learned from each other and they included those in their own revision so that the transition stage was made that much smoother, right? So block shear is also dealt with here. Right. Then the other thing is the tension force. That when a bolt is subject to tension, the plate itself that it's connected to could flex, could bend. So this is again something which was called prying action. BS 5950 refers to it, but they don't go further. They say provided it's thick enough or whatever it is, the plate, then you can ignore the prying action. So true enough, if the plate is thick, then it will be the bolts that fail. But if the plate is thin, then it could be the plate that bends and your bolts will remain, as it is. But intermediate situation, their plates could bend and the bolts could also deform, and there is that failure. So there are 3 different modes of failure that are identified, and this Eurocode gives again fairly complex looking expressions, but as I kept repeating, this can be digested and taken step at a time, and it's not that difficult to calculate. It takes time, but it can be done, and it's a realistic situation. Right, then welded connections, 2 expressions. The one right top gives you the simple method of doing it, where the direction of the stress is not accounted for explicitly. On the other hand, there is a directional method where you calculate you take the direction of these stresses on the weld into account as well, and calculate the strength of your weld. So that's again, this is simply the weld and the bolts. Now, connection behavior is a little more complex than just working out the number of bolts or the length of the weld. Now, if you take a fin plate or an end plate when you're connecting beams to columns, a fin plate is somewhat like more akin to a simple connection, taking a shear force and not being able to take much of a bending action. It can fail in 6 different ways. It can fail with the bolts failing, it can fail with the weld, it can fail with the plate bending, and so on. 6 identifiable modes of failure. And when you talk about end plate, again, there's different ways it can fail. The end plate can bend. You can have the column web that can crush. You can have the column flange bending. And there are many others. In fact, there are 16 different ways an end-plated connection can fail, right? So there is a tension zone, there is a compression zone, there is a shear zone, and each of those zones also has several components, so they can all fail in their own little way, and therefore this is a far more complex way of you have to check it using 16 different checks. But again, the code is very helpful here. There is a table separately. Of course, I have used the color code here, but say local bending of the column flange, you have a set of equations which gives you the design resistance. It gives you the stiffness coefficient. It gives you the rotational capacity. So you can work out what the stiffness of this joint is, or what the strength of this joint is. So to go back and classify your section, your joint, now you have the ammunition, you have the data which is given in this table. So then you might say, okay, is it safe to model the joint as a pinned joint when it's actually semi-rigid? Because what you do is you put the load and you assume simply supported, and you have a bending moment diagram, parabolic distribution, whereas actually it's a moment like this. Here you have a 0 bending moment, whereas here there is a bending moment, and that is also transferred to the column in a simple frame connection, right? When I say frame, it could be a braced frame situation. So there is anyway this situation that there can be a dangerous situation where the moment is transferred because of the rigidity or the semi-rigidity of that joint. So EN 19931-8 does not deal with simple joints, right? There's nothing said about simple joints. Designers are advised to consult a separate document, a publication called Design of Recommendations for the Design of Simple Joints in Structures. And there, what they say there is that if the joint has sufficient rotational capacity, they explain how you work that out, and sufficient ductility, then you can design it as a simple joint, right? Otherwise, you should take the semi-rigid nature of the joint into account in your modeling and find out the actual forces and moments in the structure. So if I were to wrap this up, then the documents to design a structure have increased. We need to know the core doc. We need to have the core document to know the basis of design. We need to know how to combine the actions. All of that is contained in EN 1990. Then we need 1991 to assess the magnitudes of these design actions. Then we need the general action EN 1993-1-1 to determine the resistance of the steel members, and the resistance of the steel joints have to be got from EN 1993-1-8. In addition to that, you need your national annexes, and you might also need to have this NCCI, that is a non-conflicting complementary information. Right? So the challenge is then to find the appropriate document and the sections and clauses within the document. The recommendations only appear once and they're not repeated, right? So that is the challenge that is faced by structural designers. So I might say in sort of final observation that the Eurocode for steel provides a more rational and consistent approach to the design of steel structures, while maintaining the flexibility of nationally determined parameters. Now, I'm sure you must be waiting to ask me, okay, there is Brexit. What is Britain going to do now? Right? So it says, despite the introduction of structural Eurocodes in 2005, some structural civil engineers continue to use the withdrawn British standards. ICE explains the circumstances for how this may be acceptable, but they say that Eurocodes represent the future as regards to safe and economic design and execution. Now, this is something I extracted from the internet. I'm quoting it as it is. This was in 2017. And it says, withdrawn British standards, the last paragraph on the left, are no longer reviewed by BSI, although they may remain competent in their approach for a time, subject to the points made below. And it says, it is apparent that the accredited engineering degrees all work to the Eurocodes, and graduates are schooled in the Eurocode approach. Hence, young engineers don't have any knowledge nor experience of the withdrawn British standards and codes. And that's true of Sri Lanka as well. Our degrees are accredited and we teach Eurocodes. So there are no engineers, or your young engineers do not have any experience or knowledge of the BS, apart from a passing reference when they're explaining the Eurocode like I did today. Then in addition, Britain via BSI is fully engaged in the current program of revising the Eurocodes, right? So as I see it, BS will stick to the Eurocodes. That's my belief. And also they say the ICE's code of conduct. Now this is important. This is I'm talking to the Institution of Engineers in Sri Lanka, the counterpart organization of the Institution of Civil Engineers, right? It draws attention to two rules in their code of conduct. It says being competent means that members have ensured that their knowledge has remained up to date. And it says all members have a duty to improve and update technical knowledge and to keep abreast of relevant developments, including new or changed statutory provisions, right? So if you are to keep abreast, then you have to be aware of what is happening in the what's happening in the later codes, and we have got to include those because that is current best practice. Now the BS codes are 10 years out of date, right? So as opposed to talking of Brexit then and what of the future, there is this contribution that has been made by John Carpenter, who is an ICE structures expert panel, British Standards Institute, British Standards Institute, as well as an ICE structures expert panel, have contributed to this. And if I were to summarize that in 3 lines, it says BSI is a member of the European Committee for Standardization, also known as CEN, and it's obliged to adopt the European norms and withdraw any conflicting standards. So wherever there is a European norm or the European standard, right? Euronorm is in French, stands for the European standards. So wherever there is one of those standards, Britain has to withdraw their standards conflicting. The CEN is independent of the European Union. So although Britain is out of the European Union, the CEN is independent of that, of the EU, and therefore BSI remains as part of CEN. And BSI is committed to the revision of the Eurocodes as stated in that previous slide. So British standards for steel over the last 50 years and post-Brexit, these are the British standards on the left over the period of 50 years. And post-Brexit, BSI will continue to adopt and update European standards into the UK national collection. UK adoptions of EN are identical in technical content to the European standards published by all other CEN and CENLEC members. So the content within this document, within this Eurocode is the same, right? Except that we call it BSEN. And similarly, in this country too, we don't have BSEN, we say SLSEN. So we have SLSEN 1993. So I'd like to leave you with this final slide or the thought. We have our SLSEN standards. Our committees have met and we have drafted the national annexes. So what is the delay? Why is the delay? When are we going to adopt it? I leave it to you to answer those questions. Thank you.
Thank you very much, Madam. And there's a few questions. One is after Brexit, Britain is no more in EU. Is there any change?
That's exactly what I answered now.
Yeah. And there's very few technical clarifications.
Yeah. I think technical clarifications we shouldn't be talking about here because this audience is a mixed audience. I can see that there are over 450 participants right now. So it might not appeal to everybody. Well, I don't know. You can ask them, but it might be too technical.
Yeah, one person is asked mode 0 and mode 3 means. I think.
Yeah, mode 0 is to do with yielding, right? Steel yields. So that is what is meant by mode 0. But where there is fracture, like even in a bolt, if there is a fracture of the bolt, then we use gamma M2. Fracture means breaking, far more dangerous than simply stretching. So we cannot use the same factor of safety. So they have identified that difference in the failure phenomenon, and therefore they include the different factors of safety. So that is something new in the Eurocode. Yes. Previously, like I said, there was no factor of safety. Factor of safety was taken as 1, irrespective of the way it failed. Yeah.
If anyone want to ask, we can even unmute the mic. if you anyone, you can raise your hand.
Yeah, there's Yoga Prajapan who has raised his hand. Yeah, go ahead and ask your question. Yeah.
Chamara, can you unmute Mr. Yoga?
Can you hear me, madam?
Yes, I can.
Madam, you're past research student. I hope you.
Yes, I do remember you. Yeah.
Madam, in the industry, in one of my project,
Yeah.
I am searching some steel sections.
Yes.
The proposed design drawings, but
Yeah.
unfortunately I couldn't find the confirmed section sizes, that mean thickness and other dimensions, and the material also they are not confirming. It is it's 275. So what are the measures available to ensure that this proposed section is we can get it?
So if the proposed section is not available, then you have to either reject. I don't know. Your role is what as a consultant, or what is your role? What are you, do you have to provide those sections?
No, that means I'm in building department. Our design section, they have proposed section design, and when I'm going to get for the BOQ, when I'm obtaining rates, those sections are not available in the market. And
yeah, then you might have to go for another section.
They are not confirming.
So either you have to go for another section, which is fairly close to that, and then check the calculations. If I were you, that's what I would do. So this is what happens. Sometimes designers select sections, but you find that it's not available, or it's going to take so many months to get it down, or whatever it is. So that's a problem that has to be sorted out. That's not to do with the code, right? That's to do with simply availability of steel.
Yeah, in that
which
case,
is beyond my control, unfortunately.
Yeah, in the material also, that means material strength also they're not confirming. So that case we have to do the
material strength. You can do some testing, and you can either you have to find out whether the material strength that has been assumed is available. Like I said, if 275 is not available, we have a fallback position that we can go for the lowest 235 value. But if it doesn't comply with 235, then I'm afraid you have to do something. You have to go for a strength that is that can be confirmed that you have a particular strength. Yeah.
The connections also, if there are issues, we have to test everything, and we have to redo the design, no?
Yeah, yeah.
Okay, thank you.
Actually, I don't see the participants. Can someone? There are 4 participants who have raised their hands.
Actually, they can speak already, okay. Or unmuted. Yeah.
Right.
Yeah, go ahead.
Here. I think regarding the last point that you raised, why we are not switching to Eurocodes, the main problem that I see is we don't have a proper training program for the people who have already left the university. I know that you all have been teaching the current generation with the Eurocodes, but for us, the training
if you make a request, I'm sure we'll be happy to run a short course on whatever the topic is. we have expertise in the different universities. So either through the IESL or through the Society of Structural Engineers, whoever, I'm sure that can be arranged if the request is made. I know Professor Jayasinghe was instrumental in organizing a Eurocode range of, I mean, he covered a lot of codes,
Yeah.
some that was about 2 years ago.
Part and a part, no, madam. I mean, when it comes to UK, they have a lot of structured programs, like the Concrete Center has continuous programs teaching the Eurocodes. So likewise, maybe the university or an institution, if they can come up with a structured program where maybe once in a
university is meant to
year.
do other things. The university's primary role is in teaching undergraduates. We also run postgraduate courses, but in the case of short courses, I don't think we can spend all our time doing short courses on a regular basis, right?
Yeah.
But we can always contribute to something that is organized by either the Society of Structural Engineers or the Institution of Engineers or whoever. Yeah. So I won't commit to university running short courses on a regular basis, but on request, yes, custom made, as it were, it can be done.
Thank you.
Engineer Nishan Gallagi.
Yes, thank you, madam. I have 2 questions.
Yes.
First one is, madam, actually, I do reinforced concrete designs using Eurocode 2. Then actually, not regarding that, actually regarding this Eurocode safety factors, I had a problem there. When I used the ProCon package, actually normally we know that the safety factors for GK and QK are 1.35 and 1.5, no? But there are 2 options. One is 2004 version and 2014 version were there. So once I use the 2004 version, automatically it gives 1.35 and 1.5 safety factors. But when I use 2014 version in that package, it automatically changes to 1.4 plus 1.6. So I had a very big doubt why it happened, but still I couldn't clarify it. It's not only regarding the steel, but regarding the Eurocode program.
Your voice is not very clear. Can I answer your question if you can write to me?
Yeah, madam,
I mean,
I'll write down.
If it's something, but if it's reinforced concrete, I'm not the person to answer. And when I'm talking of steel, I'm talking
madam.
Structural steel, right? Not reinforced,
Yeah, madam, but yeah, madam, but I got the problem regarding the safety factors.
Yes, safety factor. I'm talking of safety factors for structural steel. That is structural steel in construction, in steel structures. Right?
Yeah,
not the steel,
I know that
not the
talking
reinforcing
about
bar steel. That will be dealt with in the Eurocode for concrete.
Yeah,
yes,
that's correct. That safety factors.
I don't know when I got you right, but you spoke of reinforced.
Yeah, madam.
Safety factors for steel are given in EN 1993 for steel structures.
Yeah, madam. Okay.
Okay.
And the second problem, that if you can hear properly, so I have a big doubt why the life period is 50 years, 100 years, and 125 years for the big structures. There are a lot of massive structures are being constructed. So these number of years are they for design life, or the regarding the forces applied on them during the last
design life of the structure is, if your structure is over 100 years old, you might have to assess the the remaining life of your structure in a different fashion, because they were not designed to Eurocode, this Eurocode, right? They were different factors, and I mean, it might still have some useful life, but that has to be assessed in a separate fashion. I don't think you can we can talk of,
thank you. Okay. And one more thing, that if you don't mind, I can give one recommendation, one of my point of view regarding the question raised by the first person. I think he didn't raise that question properly. that's why you understand his question. I think he is not a design engineer and he doesn't know what is the meaning of that S235, S275 like that. As you mentioned in this program, it's a FY is if it is S235, the FY and FU are given in the tables. Then now, without understanding that, I think he is trying to find the S235 still from the market. But they are not aware about this what is S235. But if he asks the FY value and FU value, definitely he can get from the market.
Yeah, Engineer Nandan Abisurya. Nandan.
Thank you very much. I think always Dr. Mrs. Secretary, these lectures are very popular. So thank you for that. And I just want to make one is a request. Actually, now all the universities are doing Eurocodes and IESL. I am sure they accept anyone who is sitting for the professional review exam. If they submit their design report in Eurocode, IESL, I guess, is accepting that, right? So that is one. I think that is one thing we have to mention. The other one is regarding the same question that he asked. Actually, if you are doing a large steel building, you always import the steel, right? So I mean, whatever the grade that you require, you can import. If it is a small building, you have to always go to the places like Galvaland or through a contractor, see what the sections available. So I think that question was how to find the sections available.
Thank you, Nandan.
Yeah. Thank you. Thank you.
Engineer Shamind.
Good evening, madam. Can you hear me?
Yeah.
Go ahead.
Yeah. I just considering regarding some hypothetical aspect of the design optimization of the steel building, madam. So actually, in seismic aspects, there are called so we want to optimize increase the joint stiffness, madam. So to avoid the plastic information. So like in RCC design, so do we take any measures like that in that aspect, madam? Hello?
No, the joint stiffness is given purely on the joint properties, that is the details of the joint. I don't know, I'm not familiar at all. I haven't seen the seismic code. I only know that Eurocode 8 deals with seismic actions, but I haven't seen the contents of that. So I'm afraid I can't answer your question directly. But in terms of the joint stiffness, the details for end plates are given in very, very, comprehensively given. But if your joint is something else, I'm afraid, again, Eurocode lacks in it at the moment. But there is a revision which is pending. So I'm sure, or revisions are pending to the different codes. So they might include more information relating to joints. To be honest, I can't answer your question because I'm still unsure as to what exactly you want to know. In terms of some other details related to the joint, maybe you have to look at the seismic code. But if you just want to know the stiffness properties, then you have to know the joint details, like how many bolts, what's the thickness, what the the dimensions, all of those. And then you go through those calculations, you can come up with the stiffness.
Yeah, it's something regarding, madam. Now in RCC designs, we do check for the ductility and we increase the shearings. Shear. That's mean like the aspect we are getting like measures. But in steel designs, I have not seen. That's why I asked. So can we go for the optimization of in this joint and optimizing the middle, something like that?
The code doesn't say anything about that as far as I'm aware. I'm not familiar with every line of the code, right? But I mean, I know enough to impart the basic knowledge to undergraduates and postgraduates, but seismic action is not something that I have dealt with. So maybe I can't answer your question.
Thank you, madam.
Engineer Gayan Hasita.
Madam, my question is, when we design a member for a, let's say for the lateral torsional buckling, then we consider the distance between adjacent supports for the compression member. That means compression component of the member, right? But what I have seen in most of the contractors, what they do is they have these stiffener plates in closer intervals, and these stiffener plates effect to increase the lateral torsional capacity of that member. If that is a column, because of this stiffener plates, the lateral torsional capacity is increased. So my question is, does this scenario is captured in the Eurocode? Because in British code, I couldn't find any support to cater this.
What do you mean by stiffener plates?
Stiffener plates means the plates welded from connecting top flange to bottom flange of a, let's say, a rafter, something like that. Just.
What do you mean by stiffener? You're talking of web stiffness.
Yes, madam. Yes, web stiffness.
Are you talking of intermediate stiffness?
Yes, intermediate stiffness, madam. Yes. Hello.
Okay. To the web. Huh? To the web. We dealt with in the design of.
Yes, madam. Yes, connecting web.
You have to check the lateral torsional.
No, it's me.
Hello, madam.
Wait for a moment.
Sure.
Seems madam is unmuted.
We are done, is it?
Could you please others unmute your microphones? Madam, can you hear us?
Sorry, yeah, I can hear you. I'm unmuted. Sorry, you want me to be muted, is it?
No, madam. It's okay. Go ahead. There's one clarification of there, no? Are you going to answer? Or...
Oh, no, what is the clarification? This chat here. If we adopt Eurocode here, do we have seismic design supporting document books? Singapore follows BC3 documents as supportive to EN 1998. I think that's why we are still lacking to introduce the Eurocode. Our seismic expert is, I think, Dr. Sujiva Levangama, is he here?
I couldn't see him.
This has to be addressed to the seismic people. So I'm not sure about that aspect of it. But I'm talking of Eurocodes for steel, right? Are you talking here of Eurocodes for steel that you want to follow? Who's Minhaj? Minhaj, are you here? The person who sent this question.
Hello, madam. Can you hear me?
I can hear you. Yeah, it's at Minhaj. Yeah.
Oh, yeah, Minhaj here.
Yeah.
Madam, yeah.
Yes.
Yeah, I am doing the Singapore designs. Most of the Singapore designs are following the Eurocodes.
You are doing what design?
Singapore projects designs.
Seismic.
No, everything.
Singapore. Huh?
Yeah, Eurocode.
Singapore. Okay. Yeah. Okay. Yeah.
Okay.
Yeah. Correct.
For Singapore designs, they have the Singapore annexes.
Correct.
Okay. They have that Singapore national annexes to Eurocode 2 and Eurocode 3 and all the Eurocodes.
Correct.
But the problem is for seismics, they have the supportive documents called BC3.
Yeah.
BC3, but I don't think we have that type of documents in our hand now.
Yeah. So,
but if we want to introduce Eurocode to Sri Lanka, we need to prepare all the documents, all the supportive documents to follow Eurocode, right?
Yeah, but does Sri Lanka fall into that range of seismic situation?
But Singapore also low seismic area.
Singapore is also
low seismic areas like Sri Lanka.
Can we? I think you had to ask the Society of Structural Engineers. I think Nandana is here. Nandana might be able to help you out.
Yeah, thank you, madam. Basically, the Eurocode, now we are planning to use Eurocode for seismic designs also in the future. So Eurocode has separately described how to design for concrete and steel structures. That may be the reason why it is not covered in the steel codes. And is that the answer?
I think they are in Singapore. Normally, in BC3, they use the examples and what is the factors like importance factor, like annexes. Like annexes, they give what are the important factors we need to use, what are the mass we need to consider, what is the percentage of the live load variable loads mass, and other things also they have mentioned in BC3. I don't think we have the annexes or supportive documents for seismic.
You are correct. Actually, now so far the national action is not even not ready, not even started. So as an option, as an alternative, the Society of Structural Engineers has decided to form a team, including all the experts from all the universities, to discuss and prepare some guideline, at least the way forward, so that anyone who want to design high-rise or whatever the buildings for seismic, they can follow those guidelines. So we actually plan to start this exercise because the idea is anyway to use Eurocode, because the Eurocodes are very, they have very clearly explained how to design for seismic, and for dynamic or static, we have different guidelines there. So very soon we'll be working on it.
Okay, sir. Thank you.
Yeah, okay.
Madam, there was one question. You mentioned about the one book from where they want to know from where they can get that book, madam.
Where they can get the book?
Yeah. You mentioned about the Eurocode, the simplified.
The introductory textbook, my book.
Is it? Yeah.
That can be got from Expographics, or otherwise they can contact me. You can give them my number if there's anybody who's interested. Give them my telephone number, and then I can talk to them and make arrangements. Otherwise, Expographics got a stock of books from me recently, and they, I think, do online delivery. So if you contact them, they will be able to provide it.
Engineer Rupika has raised hand.
Sorry?
Engineer Rupika has raised hand.
Hi, madam. Hi.
Yes.
This is Rupika. You're my lecturer.
You're talking from Singapore?
Yeah. It's me.
Okay. Thank you for.
Yeah, it was very nice presentation. I was anyhow able to join. It was very competitive. I know your lecture is always very attractive.
Thank you. Thank you.
Thank you so much. I'm just sharing some of the experiences I have done when I do the Singapore, and then sometime I'm doing the Sri Lanka project as well. So the first of all, always, I think some of few of them has raised that question. Is the standard size. Sometimes we are receiving some drawings from the contractors from Sri Lanka, then for us to review, but we are always facing this difficulties to find the properties, the section properties. So we cannot find any database or anything, any publications. I'm not fully concentrate this question to you, since many people from the ISL also, I really appreciate if you could, if you have such publications saying that like SCI publication with the properties, and it will be very convenient for everyone. I think so. It's just a suggestion. I know at the moment I couldn't find, but if there is such thing, it's good to share through the ISL website or wherever. It's just a suggestion, and then
Rupika, if you can write, properties, if you know the normally these standard sections, they have to be made to some sort of specification, right? So either it's a Japanese section or it's a European section or whatever it is. So then there'll be the section property tables that they have to provide for that. Otherwise, from first principles, you have to work it all out. But knowing the dimensions.
Yeah, that's true. That's true. I was keeping.
But if somebody in the audience can, if you all can network and help her,
I was asked my few of my colleague friends in Sri Lanka, but sometimes even asking many people, I cannot find those things. Okay, yeah. Anyway, it's just a suggestion. If you got such a publication, please do share with us. And the second thing, madam, when I do the steel connection design, I have experienced that when I do the connection with the BS code, then if I use the same connection with a Eurocode, it's always failed. So it's mainly I have experienced that is the failure due to is the ductility requirement, which means whether it's a board fail first or the steel plate fin plate fail earlier, or that checking was not included in the when I do the BS code. It's very simple. I feel now it's always I have to provide bigger ball size and then the thicker one. So my question is, in Sri Lanka, when we design connection, do we have any software or anything, any publications or anything? I don't know whether other people has experienced this one. If I check the some connection, what I have done with BS code, if I use the now Eurocode, it's always fail. Yeah. I don't know whether anyone has experienced this one.
I think Nandan Abesurya has posted you some details about the Tata section property tables. And section properties, I think if you go on the websites, Rupika, you might be able to get some help. Have you checked the websites?
Yeah, madam, I'm asking that. I use those publication. Now I'm asking is the when if someone doing a connection in Sri Lanka, how what kind of facilities they have to check the balls? Is it publications or? Because because
I'm not involved in the day-to-day design, so I think practicing engineers, practicing steel, those who are engaged in the business of steel construction can help you.
Okay, sure. Okay, thanks, ma'am. Okay, thank you so much. Okay.
Right.
Madam, one question.
There are some other specific questions that have been asked, but I think your time is now run out, no?
Yeah, actually, we have to release the Zoom link because one event is going to start about 15 minutes. Anyway, I think there are several questions, but I think we try to use some kind of awareness so we can wind up. And before wind up, I would like to thank you because we have realized you have done great job since 2010 for this subject, and by training and developing national annexes and teaching. So we have to thank for that attempts, and from today when we have realized you gave your maximum from the start this lecture without wasting actually not any minute, rather I would like to say about not wasting any second. So we all like to have that on behalf of ISL and for you this great lecture, and we all wish you all great health and happiness. And regarding, I must thank our ISL Secretariat and our committee members as well. And regarding the participation, we reached about maximum, this is 500 today in the Zoom link. So we have to thank for all participants. And this video will be uploaded maybe 2-3 days in ISL website. Anyone can browse and anyone can get that video, browse and see the video in ISL web. So with that, I would like to wind up, and I hope we all have a good responsibility to work on this and take this challenge. And as we tell initially, and as I realize, Society of Structural Engineers are doing something, and we will see in future. With that, I would like all to great health and happiness, and good night all to.